Has anyone heard about PFNs before? Anybody? That's fine. That's totally fine. I haven't heard of it until like 2 weeks ago in class, and I thought that's interesting topic. So what PFN stands for is prior data fitted networks. So we've all heard of pre-trained models, right? So does anybody want to explain to me what a pre-trained model is?
Models are already built up and train a set of data sets, and also they have at the same time abilities to get update.
Well, yeah. I mean, what you do with a pre-trained model is up to you, right? But basically, what a pre-trained data is well, if you think about machine learning training, there is a few phases. There's pre-training, there's post-training. Pre-training means I want to take my existing pre-training data and then train a neural network, rather it's like a GPT network or any image generation network or any classification network as well. Basically, you want to encapsulate some relation of your pre-trained data towards this neural network, and that's your pre-trained model, right? You can of course do post-training on that. So going into post-training, that will give you the ability, for example, with human reinforced learning with human feedback. That's how you train a large language models to talk, to reason or think, right? So the benefit of using a pre-trained data is that it's already trained on some, let's say, for example, for large language model, it's already pre-trained on a big corpus of text. All right, so if I want to grab a model and then utilize some sort of, let's say, use it to generate some new data, I can use it with its already with its weight parameters already encapsulates some other text data that is trained upon, and then having a easier time or faster time to fit or converge that data right with my current data, and that's the benefit of pre-trained model. Prior data fitted networks is very similar, right? So instead of pre-trained, it's specifically like prior data fitted, because it's not, the data you're going to use this PFN for is not going to be the same data that you're training on, right? Very different to text compared to text, right? So because large language models are very generalized, comparably, right? They're very generalized. They're very specialized in whatever they're trained on. But let's say they're somewhat generalized because it's trained on structured data, which is just long sequences of text and sentences. It is very sometimes multilingual, sometimes trained on different topics of data, right? Either it's social media data or Wikipedia or other web scraped content. That's what your large language model is good for, and that's the edge of pre-trained data, right? It's just so encapsulating to a lot of existing knowledge. However, prior data fitted networks, its prior data is not about like encapsulating that knowledge. It doesn't have that quote unquote knowledge or the latent space present representation of what it was trained on. Rather, it somewhat only just learns to do the in-context learning that is on our specific task we want to employ these network on. And I'll get to that in context learning part. Right. So again, we post all of our meetings on YouTube, and we announce the resources on Discord. So feel free to scan the QR codes and stay connected. All right, and yeah, I kind of already did this. And our discussion is gonna be based on these following papers. The original TabPFN paper done by Amazon. The same team did TabPFN v2 and v2.5, where they extended their TabPFN that does regression and classification to do time series prediction. A closer look at TabPFN v2, MITRA. MITRA is done by Amazon. It basically takes TabPFN and then uses other ways of synthetically generating data to extend its model capability. And finally, TabICL. It's a very similar model architecture for a slightly different task. A little bit of A/B test here. What do we think about this slide? Good? No? Bad? Kind of trash? Whatever? We like it? It's pretty?
It is.
It's Gemini generated.
Mm.
And here's my thought on it. I think this is complete. Yeah, no. I think this is completely image generation. I mean, unless they did something with these texts and they only generated the background, which I mean, there's no way for me to know, but I highly suspect this is like all image generated. If it's the case, it's kind of impressive because image generation has always dealt with the robustness, and you wouldn't have a good it would like spell things very weird. So if this is really image generation, then Google has really good models. Well, Nano Banana, that's the model. But anyway, all right. So basically, what a PFN does, right? So again, the core concept is basically taking tabular data, which tabular data is basically your very stereotypical column row data sets, right? So your structured data sets, right? So your column will be any sort of attributes, and then your rows will be the data points, right? The occurrence of each point of data that you have, right? And then you're basically pre-training a model to approximate some Bayesian interface. What Bayesian approximation does, right, is basically having the former parameters of the co-occurrence probability of some certain input, and then calculating a exact output based on, let's say, given, right? So we would see very frequently, like, yeah, right here, right? So we have a probability, and then we have this like pipe symbol, basically saying, given x and d, what will be my y, right? So usually when we when we train any neural network, usually what we do is to say, okay, given my x, I want to train my model with y, right? However, PFN takes that assumption and say, hey, okay, given x, that makes sense, right? So that's everything my training set has, right? So when you train test split into two parts of your data frame, you say, hey, I learned everything from this train set, and I want to test against my testing set, and hopefully I have a low validation loss and have a very high accuracy for my test data as well. However, let's see, right? Because when you're doing the inference, when you are testing on your 20% of your train test split, your model is not attending to other data in that test split, right? It's just taking what it quote unquote learned from your training corpus and trying to make a prediction, assuming that the distribution of your data is the same between your train and test set, making a prediction on the test set as well. However, notice this D, which stands for data set, right? Data set of x1, y1, and then all the way to x and yn, right? This is my data set. What essentially a PFN does is that it takes that D, it takes that data set and say, I no longer want to just train on my train set and then test on my test set. I wanna look at my data set, and then I wanna see, okay, I'm going to find my model is going to find some co-occurrence between, let's talk about just attributes first, right? And then taking that correlation with that attributes, and then live test on what I've already gotten. That's called in-context learning. Has anyone heard about in-context learning? So how would you do? Let's adapt to a domain maybe we are more familiar with. How do I do in-context learning with large language model? Have you heard about few shots? Right.
Heard about zero shots, but
well, yeah, zero shot. What is zero shot?
means that like the model can predict something without being trained on some kind of data that we expect to basically.
Close. Well, your model always has to be trained on something, right?
Yeah, no, I mean like, but do a prediction on something that actually it didn't train on that.
Right. So during test time, right? So we already trained this model, right? So we're no longer in the training phase. We're in the post-training or the testing phase. Actually, no, post-training is misleading. Let's say testing phase. We're in the testing phase of our model, and we want to say, hey, I want to ask my large language model a question. I want it to get an answer. That is zero shot, right? What's the problem with zero shot prompting? Sometimes.
Hallucination.
Sorry.
Maybe hallucination.
Yeah, right. And by hallucination, right, it's just it just say whatever it wants to. Maybe the large language model have seen some sort of text in its training data, and then you just go about the co-occurrence very similarly. But sometimes it doesn't, right? Sometimes you're asking a very niche, very new domain question that the large language models have not seen in their training data. So what you can do is give it a few shot prompting, right? Which few shot is basically give it into the model context, right? Some similar form of data that you want your final answer to be. So you're basically quote unquote teaching the model during test time. If the user asks this question, you should answer it like this. That's called few shot prompting, right? And then you maybe not just do one, do a few, right? So that when it's actually, so when the large language models go ahead and ingest all of that prior context in your few shot as input, that goes into the transformers. So you have the KV cache and then the attention matrix. And when you build up all of that, when you ask a question in a similar form, hopefully the large language models will give you an answer of the similar form, based on how it is trained, quote unquote, like trained with your few shot prompting. That's called in context learning. The learning does not happen with the adjustment of the model weights, right? In your neural network, traditionally training happens so that the weight, the parameters of your neural network is changing. That's frozen. What is changing, however, is the latent space represented by your KV cache, right? So your large language model have a query key value, and when the key and value is being multiplied, basically, right, that's when the present representation kind of changes in its representation space. So given that context, that's the point of in context learning.
Mm-hmm.
So it's a lot. Well, what are some benefits? It's a lot more efficient because you're not like back propagating everything. You're not back propagating at all, right? So that saves a lot of compute. And also, the model may be able to, if it's a good pre-trained foundational model, you should be able to have a good ability to adjust its latent space based on your few shot context that you've given it. And yeah, so it still has a loss function during its training, and this is it. This is basically what is it called? It's a batch of binary classification is. Sorry, I forgot the name of the loss function. That's terrible. Because I deal with
Dr. Larson.
cross entropy. Cross entropy.
No, minus squared.
No, mean squared error is for classification. Regression and polynomial classification.
Oh.
Is it cross? Yeah, it's cross entropy loss. Sorry, this is just cross entropy loss, but with but instead of p theta of if it's correct, we have a probability of my my objective, right? So given my x and my data set, what is going to be my y? Yeah. Okay. Well, let's go into a little bit about TabPFN with its I already talked about in context learning, right? So it just goes through the set of roles and then take the attention mechanism. Under this is still transformer model, right? So, but it takes the set of roles and take the attention of each attribute across these roles, and then it will come to a objective of let's look at the probability of given my trained data and my x was going to be my y, and it's calculated in regard to my answer here, with my probability of this data set times the times the y occurrence of my previous examples, and then it gets into the and this is how it's trained, right? So in test time, the model's capability is basically encapsulating the data and then its state, and then just go about that, and then generate the rest of the test that you're trying to inference on. At least that's the intuition. Does it really work that way? I haven't gotten to it yet. I don't know. Maybe. I have to be honest. Here's the problem with this. Here's the problem with this thing. Right? If you think about I'm speaking in a way where it's like, okay, how this has been. But if you imagine this model before it's published, and I'm telling you, instead of your traditional way of training a neural network on a set of data to inference on that data, on the same set of data, all you need to do is take a pre-trained foundational called prior data fitted network, and then just give it some examples, and then the rest let it predict, and it worked better, faster and better than the rest of the machine learning methodologies we have. You wouldn't believe me probably a few years back. That doesn't make any sense, right? What do you mean you don't need to propagate back through the entire set of data? But no, this PFN apparently learns that Bayesian knowledge live in its context learning, and then it goes about the prediction over a single data set in your real-time inference. And now TabPFN v2 is when everything kind of hits the fan and it goes even more bonkers, right? So what if I tell you not only you just need to take the attention across the columns like we just discussed, right, without learning, we also take the attention across rows.
Double computation?
Well, quadratic, first of all.
Oh yeah, obviously.
Which is problematic, right? But second of all, what I'm telling you is that in order to predict y, right, you not only just need your x, which is kind of the assumption all along, right? Is for any neural network. It's basically I want to give this set of input of my attributes, and I want to predict this thing. I'm not only gonna give you this, I'm gonna give you like everything, like basically all of my prior data points, examples as well. Now that's weird, right? Because if you think of it, your intuition maybe as a computer scientist, as a data scientist, is probably, wait, that's gonna overfit, right? I'm giving it data that shouldn't have any co-occurrence with the rest of the data, shouldn't have any relation with the rest of the data. But given that data, I'm telling you, you may sacrifice a little bit on the computation, but it's gonna give you better accuracy. That doesn't make much sense. You're not overfitting. You're somehow generalizing and coming back to a better accuracy, and that's what V2 is, right? Is to give the ability to have another set of attention on your rows of your data as well. Yet it's still faster than training a XGBoost from scratch, and that's the scary part. And then a closer look is another paper that kind of goes into like, okay, what is really these models doing, right? So it thinks that with feature extraction that TabPFN is able to like extract these features in your data set in order to like create that separable highly latent space. And for separable, right, it's a lot more helpful for classification models if your data a latent space is separable, because then you can just kind of cut a line between the two clusters and then classify based on that. And that's why we think that this works, is its ability to extract the features and then in some sense of high dimension latent space, separate the co-occurrence. Of course, that's in general how any classification network or even regression network work, but this paper kind of affirms that, hey, this is what's going on in its inner working. And now MITRA. MITRA is kind of like this isn't like really anything too novel in and of itself, because it's just building on top of TabPFN with like some other ways of generating your synthetic data, and like just squeezing in that little bit better performance. And it's done by Amazon, so people are thinking like, yes. What's
So
up?
basically, MITRA is kind of like LM, or
MITRA is a tabular PFN. MITRA is this.
oh, okay.
Right. MITRA is not a large language model. It has no ability with text, like understanding or generation. Right. It's still just taking your table, like tabular data, taking the features of each column data, and then just taking the attention mechanism across these columns. Well, after that you have rows, but yeah. So basically, this MITRA basically, instead of like optimizing the transformer, you try to optimize the synthetic prior. So it's novel in its data generation. Yeah, what's up?
So, I'm curious about the digital complexity of the inference, like that process. Because this is a pre-trained model, right?
Yeah, yeah.
So, if I like employ this model, should I directly use this model or customize it? Or just curious about the computational complexity.
Yeah. You can't really like quote unquote customize it, right? Because and that's just because all you can't really. I mean, maybe you can. The point of this training isn't that for you to take it and then fine tune it like a large language model, right? The point of this, how this is trained over here, is that you will take this model and basically you will feed it your whole data, and then you'll take like one occurrence of your X and predict that one Y. Computationally, it's actually pretty expensive. I mean, I'm making it sound like it's not, but no, it is expensive. I try to run the model myself, and it's just taking forever to run like a small data set, and I'm like, okay, that tracks.
Is it primarily due to the ASM?
I think it's because of the attention mechanism in your transformer.
It was trained on 130 million synthetic data sets.
Yeah. but during test time, right? It's
Yeah.
still somewhat computationally expensive. But again, that kind of still beats like, hey, I'm training a very deep, very complex XGBoost model, and then going about and trying to, I save on the training entirely, and I'm only doing the test. I'm only doing inferencing. That's where this is interesting, right? Why does this work? And yeah, MITRA, how many? 130 million?
130 million.
Synthetic data sets, right? So basically, what the Amazon team did is that instead of, let's say, like improving the architecture, I'm gonna take my existing architecture and then just train on more synthetic data set, and it worked, right? It's barely better, but again, all of that computation complexity is happen during train time. So in test time, it's the same. It's basically the same as TabPFN v2. But yeah, and that's the this paper I think came out 3 months ago, and you may have heard of MITRA, but just be aware that this is just another. It's architecturally identical to TabPFN. It's just the synthetic data that it's trained on. And synthetic data is interesting, right? Because like usually you would think, oh, models trained on real world data would be good. But synthetic data, you can ensure that there's no lurking variable. You can, or like you have a consistent like Bayesian causality with your lurking variables, right? So instead of like in the real world, you can try to train a predictor or any prediction neural network, but you say like, I don't know why it works. It's just a black box, and you know it'll give me some attention score, but that's it. But this is like, well, I will create my model, or I'll create my synthetic data with the assumption of I'm capturing this Bayesian Bayesian co-occurrence here. And then I'm going to try to capture this same thing in my real world data set. Right. So it's a very rare case of, you know, a model trained on synthetic data that performs so well. This is a little bit different. I haven't tested out TabICL myself yet, but it integrates a two-stage attention with column then row and then in context learning. This is just another, I think, pretty fundamental work on how tabular PFNs really work. I don't think anyone's like done any incremental work on top of this yet, but this basically gives a bit faster inference speed on tabular data classification and regression, while not sacrificing the accuracy. But yeah. And that's somewhat essential, right? Because I was trying to run MITRA on a bigger data set. Let's say, like, I think the data points was like 30K, and then it demanded to have like 3,000 gigabytes of memory. And I'm like, buddy, I can't do that. There are workarounds, and what I did is basically just try to do a PCA on the, so I reduced the feature size, but at the same time, these models, because of its attention mechanism, is still very computationally expensive. And that's the biggest downfall of TabPFN. I'm not gonna pretend like this is the next best thing in the world, but it is. How it's working, I think should be the basis of next iteration of fundamental machine learning in structured data.
Yeah, it says here that, what's it called, the TabICL on a H100 can fit and predict a data set with 50,000 samples and 100 features in under 10 seconds.
You're kidding. Oh, I should be trying that then.
Yeah, that's how
I mean, I don't think I have a GPU as good as H100, but
need to use Google's, bro. I just connect to the
yeah.
cloud.
Okay. Well, I mean, a 2070 isn't that far off, right? That's what I have. Anyway, yeah, TabPFN 2.5 then goes around and basically, well, first of all, there's a distillation, so you can distill to a smaller foundational model, and also they use this to predict time series data, which if you think about kind of makes sense, because what time series data is, right, is basically just taking that whatever feature input you have, and then at each time iterate that and just keep going on to predict the next point. So the only difference between, like, let's say TabPFN for a data set compared to a TabPFN with a time series prediction is just that time series, right? You're basically saying, okay, I'm gonna take my previous generation and I'm just gonna keep inferencing the next point of time. And yeah, with the synthetic data is trained on with TabPFN, longitudinal or time series data actually performs pretty well with TabPFN 2.5 too. It's somewhat autoregressive as well, so you can think about how it's very, like, it's beneficial for a transformer to do autoregressive right? Autoregressive models, right? Because you have its previous context, and then you're just adding on the next one, adding on the next one, adding on the next one, just like any GPT that generates any text. Is that the last one to talk about? Yeah. So finally, just to recap, right? Without training, it's pretty big, right? Just purely in context learning is something that we have not, academics hasn't really explored on with structured data set. And then the synthetic pre-training for your approximation is something that's like it's pioneering how you can use synthetic data, right, to train a model that learns the real, let's say, statistical co-occurrence or Bayesian structures underlying in your lurking variables and other variables for your data's training, memorizing that patterns and then use that on real world data and still having the same similar result. And finally, this model, it really beats gradient boosting trees, beats XGBoost with robust and consistent outputs that I see XGBoost probably gonna be being replaced as paper baselines in a solid minute, because TabPFNs, if your data is small enough, why not, right? It's gonna perform better than XGBoost. And that's my 2 cents on this. If you want to, all of these papers that are on it are pretty good. They're all tough reads, but then it also has better I went on a very high abstraction level of how things work. All these papers give you a better insight on hey, how does your data set work? How are the transformer taking the attention mechanism across my features and database, and how are my SCMs, how is my Bayesian inference data generated, and I think the most explainable graph to make these models somewhat explainable. This is terrible. Sorry, I'm trying to get to this page. It's gonna be this graph. Can I do it? No, I can't do it. Love it. All right. Just preview being buggy. Actually, I'm not in preview. Okay, there we go. It's gonna be this graph. So basically, when your input data is when you do a multi-dimensional reduction of your input data, TabPFN shows a much smoother and more encapsulating of the co-occurrence space of your previous input on your inferencing input, right? When you give it some prior data examples, and that's gonna perform a lot better and smoother than the CapBoost and other more traditional algorithms like decision tree or Gaussian process. I also tried to do some analysis on its ability to minimize bias, because my initial assumption is that because TabPFN is so hard on taking prior data and even taking the attention with across rows, it probably have a high bias of what is just, and by bias I just mean kind of the overfitting on your existing data or existing knowledge that you have regarding to your columns. And so I run this. It may be still pretty buggy. I haven't really looked into it yet, but I'm basically running this on the accredited approval data set. It's a pretty standard machine learning data set for machine learning learners, and it's not too bad, I guess. It's generally as fair as XGBoost, so it doesn't it's not worse than the status quo, right? So you can see maybe it's harder to see with the age. Age is a little bit, well, for credit approval I wouldn't think age is too much of a issue, but for gender, I guess, you can see a little bit of fairness analysis with XGBoost, like raw XGBoost over here. TabPFN and 2D and 1D is more fair while having a higher accuracy score. It's funny that the like TabPFN that doesn't attend to the roles have a better accuracy, but sometimes in specific data sets, especially presented in the papers, TabPFN two-dimensional, like with the role attention, sometimes have a better score. But yeah, I think that's just more nuanced across my data set. And finally, MITRA is like the same level of accuracy, but a little bit less fair. But again, I think that's very data specific, and I don't think this is a solid evidence to say, hey, MITRA's better, or like TabPFN is better.
Wait, what's that crazy sexist one in the bottom right?
What the hell? Oh, you think this is sexist?
No, the XGBoost.
Oh, that's I try to adjust the threshold, but I think I just didn't have a good hyperparameter for it.
Okay.
But anyway,
it is not fair.
No, I mean, yeah, compared to everybody else, right? But that may just tell me, hey, like, it's a lot more fair to have, you know, just the models to learn themselves compared to trying to adjust it in a certain way.
Mm-hmm.
But yeah, I didn't adjust the hyperparameter. This is a very preliminary test.
Okay.
I didn't get gender to work. Sorry, ethnicity to work. But at the same time, I think it's the problem with my data, not the problem with my model. With all due respect, I mean, as we know, right, credit approval across race is not a, you know, very historically fair data. But anyway, I haven't gotten this to work. I think it's the problem with my data, but I don't have concrete evidence for or against any of the theories. So, but if you compare the TabPFN that does attend to role attention and doesn't, it's like, is it less biased? Like maybe it's like it's a little bit more biased for this, like the disparity index compared to like equal odds. So it's just two different index to compare how fair the result is. So there's nothing conclusive here, right? To tell me which one's better. I try to run that on a bigger data set. This is called Mimic, with the same code. Do I have a previous? Okay, hopefully this have my result that was run. No, it hasn't. Okay, I haven't finished running this. It's just because how big the model is, and I just couldn't finish. And this is when I said when this like demanded like 3,000 gigabytes of VRAM, and it's like I have to put it somewhere in the code just to like not only do a PCA dimensionality reduction. When did I do the reduction? I think it's the last block. Wait, no. Probably the next block. No? Okay. I thought I printed it, but anyway. Anyway, I not only had to like do dimensionality reduction with PCA down to 100 attributes, it's also I just keep reducing the max sample all the way to like 512 from like 2000. And that's tough, right? Because you want to use that, but if you can only run this model on server grade GPUs, it's like, is this really accessible for research? But that's kind of the trade-offs you get, right? With, hey, I want to reduce some time with training this model, but by doing that, I need to use a transformer. And now everything scales quadratically. And I mean, it's not NP hard, but it's you know, not too feasible with our current form of memory-intensive computing. But yeah, I also try to have a little bit more. I don't think this is really good, yeah, but I try to have a little bit of more interpretability analysis regarding to like how some of these latent work. I can't make much out of these, I guess, with regarding to this is a row attention, right? With like, for example, if it's trained on these data, how is it gonna attend to rest of it? I can't really make much sense out of this. I don't know if this make any sense at all. But
So what is that line?
what line?
Like a diagonal line.
Well, the diagonal line is self attending to self, right? So that's always gonna give a score of 1
Okay.
because you're attending to yourself. That's always gonna be 1.
Oh, got it. Like basically
Yeah.
like the zero vector on like a diagonal matrix.
Yeah, like if you have a heat map, right?
Yeah.
Correlation heat map.
Yeah,
Your
got it.
diagonal is always gonna be
Okay.
1 because, well, it's the same, so it's gonna correlate perfectly. Yeah, and yeah, I can't make too much out of this. Besides, like it seems that the space is a lot more, during the in context learning or the quote unquote training during inference, it's a lot more uniform than the rest of it. But does that mean anything? I don't really know yet. I still haven't gotten the chance to really think about this and what else can I do to really interpret what is really going on inside of the model. But if you have any ideas, let me know. I think this is a very interesting piece of research so far, and I'm trying to do a little bit more maybe on this, but so far all I've done with this model and data is pretty cool.
Mm-hmm.
Yeah, and that's all I have. Any questions, comments, concerns?